the organizers for the opportunity of being here. I'm really enjoying this meeting. It's my first time since a long time in Brazil, and I'm finding this meeting highly productive. So I'm really glad to be here. This is work I will talk mostly about 2D materials, superconductivity, graphene-based materials, and twisted and untwisted systems. And these are some of my collaborators. I will list other people along the talk. Okay, it doesn't seem to work. First of all, as this is a diverse audience, let me mention that the key problem in this new class of moire materials is how similar or different are they from more conventional, strongly correlated systems. All of them share a complex phase diagram where you have both magnetism and superconductivity, but there is the main difference, in my opinion, is that in the moire system, superconductivity is much more prevalent. You find it more often superconductivity, and moreover the so-called insulating phases are not terribly good insulators. The resistivity is always in the order of a few kilo ohms, which is way below the typical resistivity of an insulator. The main reason why they are called insulators is because the resistivity rises a little bit as the temperature is lower. Typically, in this in the strongly correlated system studies so far, the theoretical work has split into has mostly emphasized the proximity between superconductivity and magnetic phases, and then people have studied models which are basically, in general, variations of the Hubbard model with strong local models where the interaction is based on particular orbitals of the system. On the other hand, in graphene compounds, interactions effects have been very rare. Very few cases have been found. There are the graphite intercalation compounds, which are heavily doped graphene layers, and also intercalated fullerenes. They also show superconductivity. Of course, there is superconductivity when you apply a strong magnetic field, because then you get flat bands, Landau levels, and all that. And the other case famous were interaction effects were noticed was in the strong renormalization. It's like quantum electrodynamics like renormalization of the Fermi velocity of graphene, which maybe Dima Efetov will mention recent experiments later in this meeting. But let's go now to moires. As you already are very much aware of, the moires are characterized by a large, very large unit cell, which contains about 10,000 atoms, and the lattice unit is about 12 nanometers. And that means that gives a natural dimensionless parameter which allows us to classify the interactions, which is precisely how big the moire unit cell is, how many atoms you can fit inside it, which is about 10,000. And then what stands out is that most of them, as you increase the size of the moire unit cell, the effective interactions between electrons in the famous flat bands. Let me emphasize that you have, within these moires, all the action is localized into flat bands, which contain between -4 or between 0 and 8 electrons in total. So the density of relevant electrons, because the moire is so large, is very small, and then because of that, most of interactions are, when you project it onto the flat bands, are significantly reduced. For instance, if you have an intraatomic Hubbard, in order for it to play a role in the flat bands, you need 2 of these electrons in the flat bands to coincide on the same atomic orbital, and that the probability of that to happen is 1 over 10,000, 1 over the number of sites. But however, the long-range Coulomb interaction does not scale in the same matter. It scales like 1 over the square root of n, because the Coulomb interaction scales like a square over the length of the moire unit cell, and the length of the moire unit cell goes like the square root of the number of atoms. So this is a peculiarity of these systems. And the Coulomb and in addition, it was already noticed way back by Rafi Bistritzer and Alan McDonald, not only that there were flat bands in these systems, but the charges induced when you break charge neutrality by applying a gate and doping the system was highly inhomogeneous. So in addition of an average charge which you induce by applying a voltage, there was also like a charge density wave with the periodicity of the moire, which was very significant. That was already noticed by Paula Mellado and Laura Rademacher. And that means that you create a strong electrostatic potential as you go away from charge neutrality. And that creates a significant change in the band structure, because it affects in a different way electrons near the K and the gamma point. So depending on which states are filled, you will have a higher or a lower charge density wave or Hartree potential, and that in turn will affect in different ways different states in the moire unit cell. This even happens if you start with infinitely flat bands, which is the so-called chiral limit, and these are calculations with this some time ago, along with the relevant references to other people. And in a way, this is due to a fact which was partially discussed in previous talks. If you try to project the interactions onto a local base for the flat bands, you need to take into account not only density-density interactions, you need to take into account that when you put an electron in a Vanier function, which have very funny Fidget spinner shapes with a long, strong trigonal distortion, you induce changes in the on-site potential in nearby Vanier functions, and that you can define as some kind of electron-assisted hopping. So depending on how many electrons you have, the hopping between Vanier functions is changing, and that creates these huge distortions in the band structure. And that was way back already proposed by Jorge Gish in connection with high TC superconductivity as a criticism of the Hubbard model just in its canonical form. I do agree that one needs to take into account assisted hopping in the Hubbard model, probably because that just implies that the wave function of the orbitals you include in the Hubbard model may change with the amount of charge you have in them. I'm not sure if that explains high TC, but I'm sure that twisted bilayer graphene is a very clear example where this situation happens it's a very extreme case where this situation is happening. As I said, as a result, as you increase the filling, the bands are changing. And now you see the chemical potential is rising. Now it hits the central bands, and you see that they're changing very, very much. You only have really flat bands at neutrality when the valence band is filled and the conduction band is empty, and eventually you will distort the other band, and the whole effect will disappear, but only when you have filled completely the two central bands. These features have already been observed in many experiments. They are the reason for the so-called cascade, and a number of STM experiments, compressibility experiments, and so on have confirmed that the flat bands are only flat, or maybe are flat at charge neutrality, but definitely they have a width in the order of at least 20-30 MeVs away from neutrality. And all these things you can describe fairly well by doing a conventional mean field analysis, by doing unrestricted Hartree fog. You can, the Hartree part is the most important, is what is responsible for the large changes in the bandwidth, and the fog parts, the fog term leads in many cases to spin and valley polarization, which is consistent with many of the features observed experimentally. So altogether, one can say that this A Hartree-Fock picture gives a qualitative and even semi-quantitative picture of what happens in the normal state of twisted bilayer graphene. Yeah. Yeah, but you have to go well beyond the remote bands. Even the remote bands are changed. Yeah, it's a feature associated to the non-homogeneous distribution of charge, to the existence of a finite charge distribution away from half filling, and moreover, this charge distribution depends very much of where in the Brillouin zone you are. This is a unique feature of the flat bands in twisted bilayer graphene and related materials. That doesn't happen with the Hubbard model, for instance.
Or even potentially very deep in the localized environment, the potential of your atomic limit. No.
Okay. I think both of you are right. There is atomic limit, and before that, there is an independent set of graphene layers limit. You first hit a situation where basically you recover, I mean, like half an electron volt or 1 electron volt. You get the Dirac picture of graphene, and you can even neglect the intervalley scattering tunneling for these energies, and then you will get to an atomic limit. So that's absolutely the case. But what I'm saying is that the flat bands, or the so-called flat bands of twisted bilayer graphene, are indeed very peculiar, and they are not, as Oscar is saying, at all similar to the bands people have studied in connection with strongly correlated systems, where everything is happening because there are well-defined localized orbitals, D or F or whatever. Yeah. That's a good point. And no, okay, this local picture based on Barnier functions is questionable because of the abstraction and so on. So in principle, if you look at it in terms of mesoscopic physics, you're absolutely right. There should be both an excitonic effect, which goes in one direction, and also orthogonality catastrophe, which goes in the opposite direction. I totally agree with you, but it's questionable because this is very qualitative. The idea that you can write Barnier functions for twisted bilayer graphene, if you want to keep the independence of the two valleys and so on, is questionable. People have discussed this question of the of the obstruction and so on. So that picture would probably be valid for a much more localized situation and so on. You can talk a bit in terms of quantum dots localized in the center of the real space unit cell. But okay, but I would like now to turn to superconductivity, and before that I want to show to you what is probably the simplest superconductor you can cook up based on repulsive interactions, and that was invented by Valentin Hoppel and Liang Fu like 3 or 4 years ago, and it's based on the honeycomb lattice. You have spinless electrons, you have only nearest neighbor interactions, so you have spinless electrons, so you cannot have an on-site Hubbard term. And then you have a strong sublattice potential, and your near half filling, so basically one of the two sublattices is full or almost full, and then the extra electrons, there are extra electrons or extra holes. And you look at how in real space, you just make simplified hand waving argument, you look in real space how a hole or an electron can move, and how a pair of electrons or a pair of holes can move. And in order for an electron to move, if you only have nearest neighbor hoppings, it has to remove one of the other electrons which are comfortably sitting in the right sublattice. So it's you have to overcome the sublattice potential in order for that to happen. And it turns out that if there are two electrons nearby you, the energy needed to move one electron in that setup, moving from one position near the second electron to another position near the second electron, is less than the energy you have for an individual electron moving without the help of a second electron. So that is the simplest picture of electron-electron pairing in real space, and all you are including is repulsive interactions. My colleague Misha Kaznerson told me that things like that were already, as well as electron-assisted hopping. People discussed these models already in the former Soviet Union, and here is the citation. And what we did in collaboration with Valentin Coppel and Ian Fu is to formalize a bit more the model. So we wrote a kind of diagrammatic analysis in terms of pairing and Cooper pairs and so on. And what we found, and then we managed to talk about the kind of order parameter one obtained and so on. Yeah. Okay, but that's the point. These guys were very smart, and they already made the jump from pairing in real space to the formation of superconductor. And now we work in reciprocal space, and we show that by solving the gap equation, BCS. What we did is BCS. Yeah. No, not necessarily. You can have an order parameter which breaks time reversal.
What I want to ask is the local constraints or deformations will act as mobility?
No. What we did is we studied the problem in reciprocal space, in momentum space, and we linearized the gap equation, and we solved the BCS gap equation for this model in the reciprocal space. We obtain the gap as function of momentum. Sorry? That's what I'm going to talk. What we found is similar to what, let me see if this shows, no. This is that. The order parameter is in the lower right corner. F is what we call F wave, which is similar to the order parameter Andrei Chuko was talking about this morning, which means you have two valleys, two Fermi pockets, and the order parameter changes sign when you move from one pocket to the next. So you have a wave function, an order parameter, a gap function, which changes sign. So that means that a short-range scatterer, which takes you from one valley to the other, is pair breaking. And actually, it's pair breaking exactly in the same way as spin 1/2 impurity is pair breaking in an S-wave superconductor. So you can take all the Abrikosov-Volkov equation and apply it to an F-wave superconductor. Okay. So, you can think of it in terms of inter-valley and inter-valley interactions, what Andrei Chukov was calling U1, U2, and U3. This, what I call here U2, is what he called U3. And if you manage to renormalize everything, do some kind of renormalization group arguments, and go all the way to just leaving the very simple set of parameters, if you are able to characterize the interaction by a very simple set of parameters, if both U1 and U2 are positive, they are repulsive, but U2 is larger than U1, if you create a gap function such that it changes sign from valley to valley, you will have superconductivity. You make it there is a very similar argument which you can apply to the cuprates, and you get big wave superconductivity. There are two hotspots, which are the two Van Hoff singularities, and if the inter-hotspot interaction is stronger than the intra-hotspot interaction, you will always get superconductivity. And you can probably make similar analysis for the P plus minus superconductivity in the nice. You need many pockets at the Fermi level and different signs for the order parameter in different pockets. Now the F-wave superconductivity is topologically non-trivial, as I said, it's not S-wave in the strictest sense. And it turns out that if you make calculations for the superconductivity for a kind of graphene quantum dot, depending on the determination of the quantum dot, you have mid-gap states or not. These mid-gap states are obviously combinations of electrons and holes. They are Majoranas. And you can, and it's related to a famous paper by Charlie Kane and Jean Mele on edge states protected by crystal symmetries. I mean, they were not considered, well, yeah, they were considered superconductivity, and you can have these Majorana states in different configurations, typically at armchair boundaries, which are the ones which allow you to mix the two values which have different signs for the order parameter. Sorry? No, it's not chiral. Rigorously, F-wave superconductivity in a system with C3 symmetry is equivalent to L equals 0 symmetry, which agrees with what Andrei Chukov was telling us this morning. So I call it, but it has different symmetries under different operations. S-wave is just equivalent to no change at all under any symmetry operation, and this changes signs under some operation. Okay, now I will go to studies we have been doing to superconductivity in twisted bilayer graphene and untwisted systems. Let me be fair, there have been many approximations to the problem, really many. There are people who have studied phonons, people who have studied broken symmetry phases nearby the superconductivity, the skyrmion people, topological people who started from the similarities between the flat bands and Landau levels, and they have used skyrmions and related ideas in order to study superconductivity. I will mostly discuss what we have done, which is based on the long-range Coulomb interaction, which, as I mentioned, is definitely there and is very strong. It's the strongest interaction, and the technique is based on the Kohn-Lattinger approach to superconductivity from repulsive interactions. As I said, the seminal work on superconductivity arising from repulsive interactions was proposed way back by Walter Kohn and Joachim Luttinger, and they realized that in a metal you have a sharp Fermi surface, and that means that when you screen a repulsive interaction, you create Friedel oscillations, and these Friedel oscillations in real space lead to regions where the potential becomes attractive. So they looked at 2kF scattering, and they went to second order in perturbation theory, and they found superconductivity. So what I'm going to discuss is mostly that particular diagram, but those are the 4 diagrams to second order studied by Walter Kohn and Joachim Lattinger. They found superconductivity, but the order parameter had a very high angular momentum, and in addition, and the critical temperature was really low. And by the way, let me emphasize, because they said as well that if you screen the interactions, which is what is highlighted inside the red ellipse there, if you use long-range interaction, I mean, if you screen with an RPA-like bubble the interactions, it means that you have to take into account also longitudinal acoustic phonons, because the longitudinal acoustic phonons couple to the same electron-hole pairs, the same charge fluctuations, which you include in an RPA calculation. The thing, the bad luck Kohn and Lattinger had is that they studied the 3-dimensional electron gas, which is probably the worst possible case where you can find superconductivity arising from repulsive interaction. If they had studied a highly non-homogeneous case, what I explained to you before is another application of the Kohn-Lattinger technique. It's not more than that. So if they had looked to highly anisotropic or low-dimensional systems, or both, they would have found much stronger effect due to repulsive interactions. Yeah.
if they would put L equal to 1 into their formula, they would get DC 10 to minus 3 Kelvin.
I know but they didn't realize that. I agree with you. You're absolutely right. And actually, this is a paper by you, which I think you're using RG and renormalization group techniques, but similar to Conan-Lattinger diagrammatic technique, you found superconductivity as well. Now, the twisted bilayer graphene is very special because if you screen the interaction, you will have electron-hole pairs, you will have plasmons, and you will have, as I said, longitudinal acoustic phonons. In twisted bilayer graphene, all these excitations occupy the same region of parameter space, which is not the case in the typical electron gas, which basically the phonons are at very low energy, the plasmons are at much higher energy, and the electron-hole pairs are somewhere in the middle. This is what happens, This is what happens in twisted bilayer graphene. This is a calculation by Lenin Levitov and Cyprian Lewandowski. This is our own calculation where you have faint blue lines, which are, oh, thanks a lot, faint blue lines, which are the phonons. And this is a more accurate calculation without phonons from ICFO, from Paulo Jadillo Herrero, Marco Polini, Frank Oppens et al., where they also found, as expected, acoustic phonons because it's a bilayer. Okay. So these are the ingredients I'm going to discuss as possible pairing mechanism, and this is the kind of diagram we are going to study. We are only going to study the bubble diagram. The bubble diagram out of the many diagrams proposed by Conan-Lattinger. Only we are going to iterate it to infinite order because the density of states is very low and the screening is very strong. And another argument in order to justify this is famous statistical mechanics and field theory is in a way it's a large chain expansion. If you have many flavors, this is very justified. Here you have n equal 4 flavors. There's one flavor more than n equal 3, which is what they use in quantum chromodynamics. Or you can also justify this approximation in a language similar to the one used by Bowman-Pines, which basically is you have a large Fermi surface, you divide it into many patches, and you think that the inter-patch coupling is much weaker than the intra-patch coupling, and that's another way of justifying RPA. This doesn't work still. Okay, so this is what I'm trying to say. These are the diagrams. This is the diagram we're going to study. And as mentioned, we are also going to include longitudinal acoustic phone. And these are the early results. We got superconductivity. The critical temperatures were in the order of a few Kelvin, which is not bad. Also, I have to warn you that you should never trust a theoretical estimation of a single critical temperature because it depends exponentially on many uncontrolled parameters. So it's not a very quantitative prediction what we can do, but we can identify trends. That's a different matter. Okay, shit, what's happening? Okay, so these are the and in addition, the fact that we included phonons matters, and that's probably due to the fact that we are in a moire. So electrons couple not only to the first shell of phonons, the phonons which take you from one point in the Fermi surface to another, you can increase the momentum of the phonon by a reciprocal lattice vector, and it will still be coupled to the electrons in the flat bands, and that way the many phonons participate in the mechanism. As you probably know, twisted trilayers which can be reduced, symmetric twisted trilayers which can be reduced to a monolayer and a bilayer were studied next after pioneering work by Asbin et al., and they found superconductivity. and also in higher tri-layer. We did calculations and we got basically the same thing. We got superconductivity in the same, with the same range of critical temperature. By the way, the order parameter we found was F wave again, like in the case of Fu and Crepel. And now let me go to systems without a twist. You know that by now people have discovered superconductivity in a variety of untwisted systems, from Bernal bilayers to rhombohedral multi-layer with up to 15 layers, which is remarkable. And then we did the calculation and we found superconductivity, but at much lower critical temperature. The superconductivity was different. This is nodal superconductivity in the sense that besides having different signs, the order parameter having different signs in different valleys, it has nodes within each valley, and we found that it was enhanced if you added some Ising spin orbit coupling. This, and as I said, the critical temperature was like one or more than one order of magnitude lower than the critical temperature we found in twisted bilayer. Here the response function is not as complicated as in a twisted bilayer because there's no moire, it's a function. So you can go back to real space, and this is the screen interaction in real space, and as Kohn and Lattinger estimated, I mean, it's not exactly what we found, it's not exactly based on 2kF scattering because the Fermi surface is very deformed. But in any case, there are minima, and that is why you can have superconductivity. If you add spin orbit coupling, you kill one of the half of the bands. The screening becomes lower, the interactions become more repulsive, but the Fourier, so you increase both the repulsive and the attractive parts, and that's why you get an increase in superconductivity, because the superconductivity only cares about the attractive parts. It doesn't matter that the peak at Q equals 0 is stronger. So in the limit where you just have an intervalley Hubbard and nothing else, then definitely you get F-wave superconductivity again. This is a more complete compilation of results for different multi-layers. I will go back to this. And these are two experimental papers. We have participated in this one, which is Jenny Lau and co-worker. This is a collaboration between Singapore and Manchester. And what the experimentalists did for us was to tune the repulsive interactions by changing the environment, and in agreement with expectation, the superconductivity disappear as you increase the screening. That's particularly clear in the case of Jenny Lau, because they were using strontium titanite, where you can change by a lot the dielectric constant of the environment. That, by the way, leads to an interesting question, because the environment is a very convenient knob for experimentalists. They can tune the environment, and we theorists have described the environment as built up from metallic gates, which are described by image charges, and a background dielectric. And none of the two approximations are too reliable. The screening by a two-dimensional metallic gate can only be described in terms of image charges if it is really a perfect metal with an infinite density of states. Otherwise, there are quantum corrections you have to worry about. So if your gate is a graphene bilayer or even a few layers of graphite, then you have to worry about that. And a two-dimensional dielectric is not a real dielectric. At very long distances, the dielectric constant of a two-dimensional dielectric is 1. It doesn't screen at all. So this approximation we theorists have been using all the time, I think it's worth revisiting. Are worth revisiting. So this is the kind of crossover one can expect as function of the distance between charges in your twisted bilayer. And then the last thing we did in connection with twisted systems, but we were theorists, we looked at twisted tri-layers and double bilayers. And then what we can do as theorists, we can interpolate between a twisted bilayer, for instance, and thank you, and a twisted and two twisted bilayers, and the experiment showed that the TC went down immediately. So these systems, both the tri-layer and the four-layer system, are very similar to a bilayer, twisted bilayer, but as far as the superconductivity and the Hartree potential are concerned, are totally different. And that is consistent with experiments. So let me emphasize that what we are doing is to study a variety of graphene systems using the same set of parameters without adjusting parameters to each particular realization. And this is trends. This is what we find. This is comparison of theory and experiments, and it's reasonable. I must say that when we found a very low critical temperature, like in some untwisted system, we cannot exclude the possibility that other mechanisms may play a role, obviously. And this is a prediction. We were collaborating with guys in the Max Planck in Stuttgart, and they've managed to dope graphene to the Van Hoff singularity. They haven't looked for superconductivity yet, so we are predicting that there will be some superconductivity similar to the work Andrei Chukov and Leonid Levitov did. So now let me go to rhombohedral multilayers. It's as you know, people have found Longzhu at MIT has found superconductivity in a quarter metal. That seems, or according to his claims, in a quarter metal, a fully polarized valley and spin polarized rhombohedral with four layers is a superconductor. That's very unusual. But there are many. Oh no, sorry. First, let me tell you that this kind of RPA-like analysis was already studied by other people. These are recent works, and even people who were strongly defenders of the phonon idea are now turning towards explanation based on repulsive interactions. And let me also mention that we are not including, basically because technically it's very hard, the exciton-like diagrams, which will allow us to analyze soft bosons, the role of soft bosons in the superconductivity. We're trying to do it, and hopefully we'll do it. As I said, the 1/n approximation, the RPA-like approximation, can be justified in many ways, and dynamical mean field also suggests that you can get the right phase diagram without invoking broken symmetry phases. Okay, but now let's go to superconductivity in rhombohedral graphene. These are the few set of, I mean, this is now a very hot subject. These are the first batch of theoretical papers were posted. I will discuss what we have done. We combine Hartree-Fock and superconductivity. The Hartree-Fock results are very consistent. You always find a half normal metal, a half metal, and a quarter metal as function of filling and displacement field. And inside the quarter metal, we got superconductivity, and it's a very non-trivial superconductivity because there is a strong trigonal warping. It means that you don't have the Cooper singularity to help you. Moreover, most likely the superconductivity is gapless because it's not pinned to the Fermi surface. It cannot be pinned to the Fermi surface because if K is at the Fermi surface minus K, is not going to be there. And so in some way trigonal warping plays the role of a pair-breaking perturbation in this wave superconductor. These are other works. I mean, as I said, this subject is incredibly hot. Everybody is writing theory papers. Let me mention this. There's a very nice paper by Long Fu and co-workers here, where they propose another possible phase diagram based on vortices in real space in the absence of a magnetic field, and I don't think it can be ruled out. These are our most recent results, going beyond 4 layers, and the phase diagram is very robust, no matter how many layers you include in the calculation. This is only Hartree-Fock, this is not superconductivity, we haven't finished those calculations yet, but we always get full metal, half metal, and quarter metal, and sometimes some nematic phases where the C3 symmetry is broken. And these are even more recent experiments confirming superconductivity in rhombohedral multilayers with different number of layers. And now the question arises, how many layers you need before the bulk bands swamp completely these interesting non-trivial phase diagrams and dominate, and you lose superconductivity. And this is kind of very speculative, we're working on it, but basically it's infinite. The rhombohedral system can be mapped onto, if you simplify the bands as much as you can, without losing completely the physics, can be simplified onto a Schiffer-Higger model, which has a topological phase and a non-topological phase, depending on the parallel momentum. And if you're in the topological phase, you always have a flat band at the top and at the bottom surfaces. And this flat band will persist no matter how many layers you have. And moreover, if your number of electrons is such that your Fermi velocity, your Fermi wave vector, is below this point where the bulk bands go down, then you have a large energy gap with the bulk bands. By large, I mean 400 MeVs. So that means that if your number of your electron density is such that it doesn't leave this region near the K point, you will have this kind of normal metal, half metal, quarter metal, and presumably superconductivity all the way to infinite layers. And moreover, the density you need is related to this wave vector here, and it happens to be 10 to the 13 electrons per square centimeter, which is very large. As I said, the thing is that if you are in this region, the red bonds in the Schiffer-Higger model are very small, and basically you have one state here and the other state there. And technically it means that rhombohedral graphene is what is called a nodal line semi-metal with a drumhead surface stage. And let me just mention in passing that Lisello has recently reported experiments according to which the spin orbit coupling in rhombohedral graphene is in the order of 0.1 millivolts, not microvolts, which is the case for a single graphene layer. That's the Meyle model, and I did some work on that. So let me summarize. Yes, I wanted to tell you, if you classify the interactions of twisted bilayer graphene, you realize that the Coulomb interaction definitely is there and is very strong. You use a very conventional and standard set of parameters, and you get a trend for the superconducting, the critical temperature, which fits reasonably well the experiments. And if you now go to untwisted systems, there is this very new and very interesting topic, which is superconductivity in a quarter metal rhombohedral multilayer. And that's it. Thank you very much.
Questions?
Thank you. In the rhombohedral, you say that, well, independently on how large is the number of layers, you have these flat bands, but which is, or do you have an idea of which is the optimal number of layers to have the different type of correlated effects up to higher temperatures?
Excellent question. And this is all speculative because we don't have complete results to understand it. The bands are always slightly dispersive. They are the flat bands you see there. They have a quadratic trend due to a parameter in the bands called gamma 4, which breaks electron hole symmetry. So presumably you will always have this quarter metal phase at sufficiently low filling because you will occupy just the bottom of this quadratic band. Now, whether in addition you will get superconductivity is a different matter, and that's more complicated to answer. But definitely, I think you can go to many layers and still see magnetic or polarized behavior. But again, this is speculative. We haven't gone beyond 15 layers at this moment.
Yeah. Okay. The question will be a little bit technical, but I will accept non-technical answer. So when you do diagrammatics, when you do calculations, you essentially take bubbles and some bubbles, justifying it by large n. On the other hand, if you look back into Kohn-Latinger, Kohn-Latinger was a way to also describe spin fluctuations.
Right.
And for example, spin-mediated D-wave superconductivity. And this is different set of graphs, maximally cross diagrams.
Well,
now,
these ones.
Well, maximally cross diagrams that give you interaction by spin
you switch the green arrow.
Yeah, you can put it this way.
Then they will what you say.
Maybe putting the connection to Lewis talk. In your case, so the idea is that spin fluctuations are totally irrelevant.
No, not at all. What I'm saying is that the long-range interaction is enough to describe the main trends for a variety of twisted and untwisted systems. For me, the most striking result is the fact that a twisted bilayer is one thing, a single layer on top of a bilayer is totally different with respect to superconductivity. I'm not sure because all these systems, a double bilayer, one layer twisted, they also have so-called insulating phases, but they are not good superconductors at all. And it is related, speaking of that, to the strong hard-tree deformations which are specific of a bilayer or a symmetric tri-layer or a symmetric four-layer system and so on. So the twisted bilayer and it stands out because of these strong deformations of the bands. And in addition, if you ask, it's too bad he's not here, Andrei Bernevy, if you ask Andrei Bernevy whether his topological condom model works for a twisted tri-layer, which is not symmetric, or a twisted double bilayer, he will probably tell you it doesn't work. So there is a relation. You can either say that the strong hard-tree potential is a proxy for how large the critical temperature is going to be, or the validity of the twisted Kondo system is a different proxy, but basically equivalent for the existence of superconductivity in twisted systems.
So in your position-dependent interaction, you were showing there's a particular distance where there's attraction developing in your V of R, and I wanted to ask, what is a setting that physical scale in case of the non-Moiré system?
So you're talking about non-Moiré systems?
Yes, but you have shown the Moiré value.
Yeah. To tell you the truth, we don't know. This is probably related to the Moiré unit. I don't think it's a 2kF Friedel oscillations because the Fermi surface is very distorted. It's near a Van Hoff singularity, a trigonal deformation is very strong. It's something related to the Moiré, which implies something. Oh, no, sorry, this is untwisted. Implies something for the response function. The response function is also anisotropic, so we cannot tell you. This is a good question.
So you went pretty fast on the quarter metal superconductor in rhombohedral tetralayer. Can you say what do you expect the properties of this superconductivity to be?
Okay, it's a mystery.
Does it require a threshold of interaction?
It's a mystery for, okay, if I tell you a little bit more of the history, we did our Hartree-Fock calculation, we looked for superconductivity, we didn't find any superconductivity at all in the quarter metal. Then we realized that if you do a Hartree-Fock calculation, the density of states at the Fermi energy is by definition 0. It decays logarithmically to 0. It was well known already in the 80s.
Because
it's due to the long range.
The filling is integer?
No, it's just you. In Hartree-Fock tends to open gaps or to widen gaps. In the case of a metal, it creates a dip in the density of states at the Fermi energy, and the dip it goes all the way to 0. and that is due to the long-range Coulomb interaction, both in 3 and in 2 dimensions. And in 3 dimensions, it's discussed even in the book by Maham. Okay, then we had to resort to this RPA-like combination of terms, which is a bit like GW0 in terms of band structure calculations, and we recovered superconductivity. But definitely, there is no, even if you go beyond Hartree-Fock, you don't have a Cooper pair singularity. So there was no reason, and there should be some threshold beyond which there is no superconductivity. It should be a first order phase transition, because if you don't have the logarithmic singularity, there is no divergent susceptibility which guarantees that you will have superconductivity as function of a parameter which is being increased slowly. So this is just a numerical result, which we don't fully understand, but definitely there is superconductivity.
And do you get it to be gapless or gapped?
That's a good thing. That's another thing. In order for superconductivity to be gapped, you need to start with that plus k, and you have this order parameter to be pinned at the Fermi surface, and you need to have plus k and minus k to be at the same energy.
Yeah.
So it will be, it will have no gap, that's for sure.
It will be gapless.
Which means that it will be very fragile, and a lot of perturbations will destroy it. So it's a mystery why it has been observed in the first place, but it has been observed and we have found it numerically. That's all I can say at this moment.
Any other questions?
So it was a bit too fast for me, but I maybe I'll ask a very dumb question. Maybe you even answered that already. If you go back to the Schrieffer-Higger kind of case, I'm just trying to relate that to Schrieffer and Higger. What's the point you're trying to make here? Because in the original paper, they're trying to study polyacetylene, which has an alternating bond, but the most important point there was that it has solitons as being the conducting mechanism. So
in addition, that's a good point. No, here what I'm trying to say is that the Schrieffer-Higger, I mean, for each K parallel, a very clean rhombohedral graphene can be split into many one-dimensional problems, one for each K parallel. Each of those systems is a Schrieffer-Higger model. So then, and it has a topological phase and a not topological phase. So irrespective of whether you have a kind of inversion of the gap in the middle, you will have localized states at the top and at one end of the chain and at the other end.
Right, but you're not worrying about solitons here, right? And it's just the zigzag, the bonds being different, which is just a Pyre state. That's basically what it is, right?
However,
it's spirals. But
So I'm only worried about the edge states you get at the top. But it's true what you say, that if you create a stacking defect, that may play the role of a soliton. And then you will have, in addition to a two-dimensional electron gas at the bottom, at the top, you may have somewhere in the middle another two-dimensional electron gas.
Okay, so and then this is the final thing, is the other thing about the, I don't even remember what the slide was. I think was when you were talking about the Coulomb interactions generating superconductivity and so on as you change density, right? The screen case, because you have a gate and you're screening the Coulomb interaction. Is there a regime where there's competition between Wigner crystallization and superconductivity, or not?
That's a fair point.
Because
nobody knows. Wigner crystals have not been observed in twisted systems. The experiments I refer to here are for twisted bilayer. There's no evidence for Wigner crystals in twisted bilayer. There is evidence, or some evidence, for twisted.
But if the Coulomb interaction plays an important role, then you can change the density, right? You would expect, as a function of density, with the screening, there should be a dome.
There is a problem. The Moiré systems are way dirtier than the rhombohedral and twisted systems. And I imagine that the Wigner crystal is very sensitive to disorder. That's a possibility why people have no good evidence for Wigner crystals in twisted systems. But definitely there is not. But we haven't checked for that.
Not
so
even
I
the
cannot-
disordered one, right?
Okay, let's thank Paco again. Now we have a break until 4:10. See you back here.